Hi, this is Faik, and with my partner Rachna, we are implementing a elliptic curve-based additively homomorphic encryption. So the basic idea is, let's say there are some sensor network. So different sensor will be aggregating some data, and that data will be sent to a base station. Now here the base station will have a secret key, and we are basically doing this whole thing in a public key cryptography. Now that base station will be sending a public key to the other sensor nodes, and those sensor node will encrypt their data using those public key and will be sending to a intermediate sensor node, which will be aggregating the all encrypted data in the encrypted domain. And that encrypted data they will send, that encrypted aggregated data they will send to the base station, and that base station will decrypt that corresponding data. So this whole operation is being done mm, uh, by property of elliptic curve based encryption, that is called homomorphism. So we are using a additively homomorphic encryption. So what's the property for this? That is, let's say we are adding two messages in encrypted domain. So the underlying messages of those encryption will also be added. So that's the basic idea. So in elliptic curve domain, so the basic operation, so the main operation is the point multiplication, because so for every encryption we define a hard problem which is tough to solve. So based on that only we implement some encryption method. So here the hard problem is this one, this kp equals to q. So if we are given is multiplied form with a scalar of a point at the elliptic graph, that is p. So we are multiplying the point p at the elliptic graph cryptography with a scalar k to get a q. So it is told that if we are given a q, then it is hard to get back the p. So this is the whole idea behind this elliptic graph cryptography. So we'll find this point multiplication to generate the ciphertext. So how we are doing? So the basic idea you can see from this 23 into p. So we divide this whole operation into multiple doubling and addition operation. So we are basically implementing this whole point multiplication by some point doubling and point addition. So the formulas for the point addition and point doubling, those can be seen as follows. These all things are implemented in an underlying prime field. So in our case, that prime field is 256 bit. So let's directly go to the code for that. Huh. So this is the code for this. So I'll quickly go through what's happening here. So here in this portion, so we are generating the secret key here, so that G into SK is being multiplied and we get the H. So this is my public key. So using that public key, first we are encrypting one message in a sensor node, let's say that is 16 here, and later we are encrypting another message that is 25 here. So for the first message, we get C12 or C11 and C12. These are the ciphertext. And for the second message, we get the C21 and C22. These are the ciphertext. So now one of the intermediate sensor node will be aggregating these two messages to get the corresponding aggregated ciphertext, that is C1 and C2. So we are basically doing point addition of the C11 and C21 and C12 and C22 to get the C11 and C22. And next, from that C11 and C22 at the base station, we are decrypting the message back. Now after decrypting, what we get, that is message into a generator function G. That is given here. That message into G we get back. So that we are printing later also. Now from that M into G, we do a basic search operation one by one. So this search operation is not that much optimized, but for our work, it is sufficient. So using this search operation, we find the whatever message we have encrypted. So we'll run this code now. So we are setting up a putty so that we can get all the intermediate values printed on the screen for better understanding of the operations. So this thing will take a while. This is the main reason while moving towards some hardware accelerated encryption. So this thing we can infer from this project, that is this whole operation will take some finite time. Now that time also we are measuring. So meanwhile, I will explain how we are measuring the time here. So what we are doing here is at each important operation, that is let's say key pair generation, we are starting a timer before that, and after the operation we are disabling the timer. And this timer cycle count we are incrementing inside a interrupt routine that is inside this GPTM module. So inside this interrupt routine, whenever it comes, then this timer cycle count will be incremented. So what it does is we are initializing the timer count at 65535, and till it comes to 0, it will decrement, and when it comes to 0, it will go into the interrupt routine, and that timer count will increment. And that timer count, what you're doing here is we are shifting left by 16 bit. So what it is doing here is we are multiplying this whole thing by 65536. So this means one complete count we have done, and what's the extra we are counting by the start minus stop. So this stop is the ending time and start is the starting time. So using this we are measuring the time, and we are measuring the time at 4 stages. One is key pair generation. Another is the encryption time of one message, that is the key pair generation plus encryption time of a message. Then what we are doing here is we are measuring the time for the data aggregation, that is the encryption ciphertext 1 plus ciphertext 2, that point addition. We are measuring the time, that is CC aggregation. Then at the base station for the decryption, we are measuring the time, that is CC decrypt. Then the searching time we are finding, that is from the MG, how much time it takes to get back the M using the linear search. So let's see how much putty goes. Yeah. So here what's happening here is, so this is the secret key we have used, that is the 76543210. So this you can see, and the public key. So using this secret key, we generate the public key at the base station, that is X into G. So X is the secret key multiplied with the G, that is the generator function. So this was the main point of the elliptic encryption, which I explained earlier. So the algorithm here is from this, if I'm given this XG, it's hard to get back the X. So that's the whole idea. Even if some eavesdropper comes in between and gets hold of this XG, he or she cannot get back this X easily. So this whole problem is exponential time computation. So so the public key we are printing here using this all printing is being done using UART, and this public key has two component. One is the X coordinate, like this is in affine coordinate. So each coordinate is 256 bit. So we are printing it in hex. So this is the X coordinate and this is the Y coordinate 256 bit. So you can see. Now here at one base station, we're encrypting one message, that is message 1. So that message 1 is 00010. So this 10 means this is 16, right? Now this 16 message we are encrypting, and we are getting a ciphertext, that is C11 and C12. So this pair of ciphertext we generate from this message 1. So how we generate this C11? So this C11 basically is a random number R multiplied with the generator function. And similarly, C12 is that random number multiplied with the public key. This public key is called H. So that public key we multiply with a, like, these all multiplication are scalar point multiplication in elliptic curve. So that R into this H we do, and we add with the M into G, where M is the message and G is the generator function. So thus we get the C12. So these two ciphertext, not these two ciphertext, this pair of ciphertext, the C11 and C12 we get for the message 1. Next, we are encrypting the message 2 in another sensor node. That message 2 is 19. So this is 16 plus 9, this is 25. So we are encrypting 25 and we are getting a pair of ciphertext that is called C21 and C22. So the next step is we are aggregating these two ciphertext to get a aggregated ciphertext. So we are basically doing a point addition of this C11, C12 and C21, C22 to get the resultant C1 and C2. So this aggregation is being happening at the encrypted domain. So this is the whole of idea of this whole project. So this aggregated ciphertext can be seen. Next, at the base station, we are decrypting from the C11 as C1 and C2. So how we are decrypting is this C2 minus C1 into the secret key will do to get this M into G, this message into G, where the X is available with the base station because base station is at first generating the public key using the secret key. So base station is having the secret key. So base station only can decrypt, no one else. So yeah, so from that decryption method, we are getting the M into G. Now, as this message is very small, so using a search operation, we get back the corresponding message. Now, the maximum value of message here is 63. So from that search operation, we are getting back the message equals to 41. So we can verify that that is 16 plus 19, so equals to 41. So yeah, so this was the whole operation, and also we can see the corresponding time, how much it takes. Uh, so what we can do is we can pause and check the values of these corresponding times. So as you can see, this CC is taking this much time. So this is quite large. So that's the whole idea that for encryption, this elliptic curve encryption, it's better to have a hardware acceleration. So similarly, you can see CC decrypt, CC search, and CC aggregation. So this whole time, this much time, this whole code is taking. So yeah, that's it. Thank you for listening.